Hi guys, I hope you can hear me. I hope you can see me. Okay, can somebody confirm you're there? Audio?
Yes.
Fantastic, right. Last week well, first of all, this week we've identified 4 major areas which should be of interest to you with respect to the exam. And those were the distance classifier, the second area was the analog neurons, and networks. The third area was digital neurons. And the fourth area was image processing. Gosh, I can't write this morning. Image processing. And we dealt with that one last week, and I dealt with digital neurons last week. So let's just have a lightning review of the other two. First of all, the analog neuron. Often referred to as the McCulloch-Pitts model. After the two guys who first proposed it, and it's been around an awful long time. It's around about 1950s the first paper was published on this. And the idea of the analog neuron, go back to the natural system, a natural neuron, which is our inspiration. Here is a cell with spikes on the input and an output. There's my output Z. There is my inputs coming in. I1 to IN can be represented by a vector. The question is, what on earth goes on in the cell body? What is the function of that neuron? And the McCulloch-Pitts model proposes that the inputs, which are analog, unlike the binary inputs for the digital net, the inputs that are analog have varying degrees of importance. So that can be modeled by having, let's just take 3 inputs for simplicity, I1, I2, and I3. There's my input vector. And to determine the level of significance, the importance of these inputs, we have weights. And the weights will be W1, W2, and W3. And this, of course, can be expressed as a weight vector, W. We can combine the outputs of those weighted inputs, and the simplest way is to sum them. And we can have a threshold to determine which of 2 classes that they belong to. So what we are actually calculating at this point here is the summation I equals 1 to D over all dimensions of Wi, II. In this case, it would be W1 times I1 plus W2 times I2 plus W3 times I3. Now, how does this behave? Well, even with 3 dimensions, it's difficult to draw. So let's just go down to 2 dimensions. and this can be dimension 1 and dimension 2. And input patterns will be vectors. Let's have a class of patterns here, and we can draw them as points. So that's class A. And let's have another class of patterns down here, B. And A is going to be equal to A1, A2. And for this pattern, that would be A1. This would be A2, second dimension. For B's, I've got my colors around the wrong way. Never mind. B is going to be vector B1, B2. That gives you your points. So B here would be B1, B2. And if I wanted to separate those, if I could find a line, the A class can be classified as a threshold above a threshold of 0, i.e. a positive response coming out here. And the B class can be classified as a negative response. And that decision surface can be defined as the weight vector, which is not unique. There are millions of them. It has to be at right angles to the decision surface. The decision surface can vary, so there's lots of solutions. And the weight vector would have some negative coefficients. So let's extend the axes. This would be W1, which would be positive, and this would be W2, which is negative. Right, so that's the behavior. Now the idea, we've seen a decision surface with the classifier. We're not doing it by distance anymore. We're defining one vector, one weight vector, which will define the decision surface, and it will separate the positive from the negative response. So if I have an unknown pattern, let's take pattern X there. There is the vector point. This would be X1. This would be X2. And to classify that, the calculation I'm doing, summation I equals 1 to D of Wi, is a vector definition. It is equivalent to the scalar product of two vectors. And in 2 dimensions, it equals the mod W, the mod I, cos theta. And cos theta is going to be the angle there. So that is going to be theta. And you can see a positive response will be occurred if theta is less than 90 or greater than 270 round here. And a negative response if theta, as it is in this case, is greater than 90. So that's how you get your positive and negative responses. If you can find the W, you can use it to test on any pattern, single operation, and to determine whether it's positive or a negative response. So that's the basis of the process in a single neuron. Right, how do we get W? And this is training. And the idea is we use error correction. Oh, go away. And error correction is if an error, update, and an error comes from a training set where you know the classification, update the weight vector, becomes the original weight vector plus C, a fraction of the input pattern that is in error, and that's also a vector. And this is basically Hebbian learning. Now, in the lectures, we calculated and an error occurs where W.I equals S, and S is the wrong sign. i.e. you're expecting a positive response and S is negative, or you're expecting a negative response and S is positive. And we did a bit of mathematics, which would enable us to calculate C, and we found a correction factor C equals minus 2S over I dot I. This is the correction factor, this is the error from the current input pattern, and this is the current input pattern. And if we use that, we can guarantee that we have a new weight vector that will get the previous pattern correct. So we're correcting the error, but of course it might introduce early errors. So that's the theory behind the training. That is tricky, and you really need a computer to sort that out, a lot of number crunching. So there is an approximation. And the approximation is let C equal plus or minus 1 when you get an error. And this would be if S is, if a positive class pattern, training pattern, and S is negative, then C equals plus 1. Positive class is giving a negative response, make it more positive. And the other one is for the negative class, S and giving a positive response, then C equals minus 1. Negative class, we want to reduce the weight vector to make it more negative. So that's the basis of approximate training. And this can lead to some interesting examples for testing your knowledge and thinking of exams. So a typical pattern. Let's take some 4 pixel images. I think this is different from the one I had in the lecture notes. I'm pretty certain it is, but it's a similar type of problem. And that is 2 reference patterns, 2 training patterns of one class. And let's change the color. There is going to be that pattern and that pattern. First of all, you arbitrarily decide which class they're going to be. Let's have this positive and this negative. It could be the other way around, but that's a choice, a labeling you have to do. Right, now in the notes, we started off with a training example with initially a 0 weight vector. Now, should this happen in the exams, you will not be given a 0 weight vector. And where the personal data comes in, your weight vector will be generated from your student number. So supposing we end up with a personal weight vector, this is a new example. Supposing we had a weight vector of W equals 1 minus 2.5. We can have integer numbers and fractional numbers. Let's have another 1, and let's have there's a decimal place, 1.0 and 1.5. So there is my 4-element vector. Now, pattern data to vectors, scanning from the top left, we would get 1, 1, 1, 0, which is this pattern here, and we would get 1, 0, 1, 1. Those are your binary vectors. They're not 4-bit numbers, they're binary vectors. And for the red class, we would get 1, 1, 0, 1, and 0, 1, 1, 1. Again, vectors. So this is the pattern I, vector I. The class, which you have assigned. Class here is positive, positive, negative, negative. And we calculate the scalar product of the weight vector, the correction factor if needed, and the updated weight vector. And for a training iteration, We start off with the initial weight vector. The scalar product with the input pattern is going to be 1 times 1 is 1 plus minus 2.5 will give me minus 1.5 plus 1 is going to give minus 0.5. So the scalar product is going to be minus 0.5. It is wrong. Should be a positive class, negative response. So we're getting a wrong response. C, positive class, negative response. C is plus 1. And the updated weight vector is W plus the input vector, and it will be 1 plus 1 is going to be 2. Minus 2.5 plus 1 is going to be minus, don't disappear, minus 1.5. 1 times 1 is going to be 2. And 0.5 plus 0 is 1.5. So there is my new updated 4-element vector. For the next pattern.
Sorry, John.
Yep. Go on.
With the correction factor, did you multiply C by I?
No.
I think I missed what you did to get.
Okay, let's go over that again. Input vector. It is a positive class pattern. We've defined it to be positive, right? We calculate the scalar product of W dot I, which is W1 I1 plus W2 I2 plus W3 I3 plus W4 I4. Go through that calculation. It is going to be 1 times 1 is 1. Let's write it down there. Plus 1 times minus 2.5. So it's going to be minus 2.5. Next one is going to be 1. And the last one is going to be 0. So the response is going to be, let's add those up, that should be a plus there. It is going to be minus 0.5. Minus 2.5 plus 1 plus 1, minus 0.5. There is the response. It is negative. Positive class needed. We are using the update of the weight is W prime equals the original weight plus CI. So I am now adding the input pattern because C is equal to plus 1. Negative response, we want a positive response, add, and so we are going to have the original weight vector, which is 2 minus 1.5, 2 and minus and 1.5. And we are adding to that 1, 1, 1, 0. 1, 1, 0. Add them up. Silly me, I've made a mistake. That's the updated weight vector, isn't it? This W there is this one here. It is 1 minus 2.5, 1 and 1.5. This is W and this is I. W there, the initial weight vector. There is your input pattern. Add them up. We are going to get 2. We are going to get minus 1.5. We are going to get 2. We are going to get 1.5. So that is W prime. That is the new weight vector, and that should be the one which is in there. Okay?
Understood.
Right. Great. Fantastic. Now, the new weight vector. The scalar product of the new weight vector with the second positive class pattern is going to be 2 plus 0 plus 2 plus 1.5. It's clearly going to be positive. What's going to be 2, 4? It's going to be 4.5. Is it 4.5? 2, no, 4, 5.5. Ah, don't disappear. Plus 5.5. Positive. Positive class. No action. No update of the weight vector. Now the same weight vector, the last value we updated, with the first negative pattern. Shrink that down a bit. So we're now multiplying 2 times 1 is 2. 0 disappears. 4, 5.5. So that is also going to be 5.5. Is it 5.5? 2. Oops, wrong line. Sorry, I thought it was wrong. 2 minus 1.5 is 0.5. 0 and 1.5. 0.5 and 1.5 is 2 plus 2. It's a positive response. It's a negative class. We need to update the weight vector, make it negative. C is minus 1. We will now be subtracting the current pattern from the current weight vector. And let's do that separately. So the current weight vector was this. We're now subtracting the current input pattern, which is going to be 1, 1, 0, 1. Subtracting the elements is going to give me 1 minus 0.5 to 1.5. And that will be your next iteration of the weight vector. So the new weight vector goes in here, and that is going to be 1, 0.5, 2, and 1.5. Let's get rid of this. It's in the way now. Oh. And for the last pattern, it's the scalar product of the latest weight vector with the next input pattern. It'll be 0. Second element is 0.5. Third element is 2. Fourth element is 1.5. 1.5, giving me 1, 2, 3, 4. So the response is plus 4. It is wrong. Negative class, positive response. C equals minus 1. And so we now subtract the current pattern from the latest weight vector. Let's do that over here. It is going to be 1, 0.5, 2, 1.5. And we are subtracting the current pattern, which is this one here, 0, 1, 1, 1, giving me 1 minus 0.5, 1 plus 0.5. So there is my next update of the weight vector. Is that correct? Right, so that would then go in there, and we would have 1 minus 0.5, 1, and 0.5. So the final weight vector after the first iteration is W equals 1 minus 0.5, 1, and 0.5. And that is the iteration, that is the weight vector after the first iteration. Now it's changed. We started off with this weight vector. It's changed 1, 2, 3 times in that iteration. And of course, the last weight vector, it guarantees to get the last pattern correct, but it might have introduced errors previously. So you then have to take that weight vector and go through the training set again and update it for each error. Now, in an exam, I would not expect you to do any more than 3 iterations. Could be less. In practice, because you know of the limitations of things like linear inseparability, it might not even converge to a solution. But in practice, it would certainly take more than 2 iterations. So in the examination, should this be a question, you would be asked to update the weight vector for 2, possibly 3 iterations, and then use the weight vector. Now, if that was the final weight vector, and I had a test pattern, let's choose one that's not in the training set. Let's have a diagonal. That's not in the training set. No, that's good. And that will give me input pattern scanning from the top. It would be 1, 0, 0, 1. And if my weight vector was 1 minus 0.5, 1.5, there is my weight vector. To classify this pattern, we would get W dot I, and that is 1 plus minus 0.5 plus 0 plus 0.5. And adding those up, it is going to be 1, and it is positive. So that pattern would be classified as the positive class. So the pattern we put was that pattern. Subjectively, yes, I guess that part, oops, I mean, it's very low resolution, but if I take this part of the image, that has occurred there. So it is similar, more similar, I think, to the positive class than the negative. So even with a simple example like that, then it is doing something vaguely intelligent. It's a start. So that would be training. Then further properties. You need to consider the bias. And the bias actually shifts the decision surface away from the origin. With this particular model, all the decision surfaces must go through the origin. The bias will allow that to move away from the origin. So you can then have a problem such as this, where I've got a class of patterns there, which are class A, and I've got a class of patterns there, B. And clearly any line going through the origin will not separate them. But if I don't have to go through the origin, straight line, kapang, plus minus, the solution is possible. Then there is nonlinear it's curved, and this will lead us to higher order functions. And keywords there would be the phi machine and the quadric machine. And And finally, the other major topic I looked at was linear inseparability. And the classic problem there was the XOR problem, which is not only a logic gate, it is an analog function. XOR problem occurs when I've got two distinct sets of data. Supposing I have a class of patterns A, which has two subsets, and a class of patterns B, which are two completely different distinct subsets, but looking at that, a single linear line will not have the A's on one side, the B's on the other. And that leads us to a multi-layer structure. And that was known as the MLP, multi-layer perceptron. And the perceptron was a name invented by a couple of guys called Minsky and Papert to describe these devices. It's not perception, it's perceptron. P-E-R-C-E-P-T-R-O-N. So if you see perceptrons, they are McCulloch-Pitts neurons, they are analog, and they have weight. So that's a lightning tour of the analog net. Half an hour left, just under half an hour. So let's have a look at the fourth major section, which is image processing. Image processing is a useful tool for normalizing data to make the recognition easier. A whole family of image processing techniques, single pixel, sometimes called monadic in the literature. And the two big ones are the image shift, which is equivalent to brightness control, and this is taking a pixel Bij after shift equals the input pixel Aij plus a constant. So this is the output pixel, and this is the input pixel. And that is a simple add, but there is one condition. We have to clip the output because image systems are fixed point. So image range Bij has got to be somewhere greater than or equal to 0 and less than or equal to 2 to the n minus 1, which is n bits resolution, which for exam questions would be 0 to 15, that'd be 4 bits resolution. And this is sometimes referred to as white. This is sometimes referred to as black. For real images, grey images, it is going to be 0 to 255, and that's 8-bit resolution. So going back to here, if B has to be within a certain range, then the exception Bij equals W, or 2 to the n minus 1 if we've got n bits resolution. If Aij plus k is greater than W. In other words, we can go up to white, we can't go beyond white, and so the screen, if you keep doing a shift, will become whiter and whiter as you increase the magnitude of the shift. So that's image shift, and the other one is image multiply. and this is equivalent to contrast. And the image multiply is the output pixel is equal to Aij, this time times k. You're doing a multiply rather than a addition. And of course, it also clips equals W if Aij plus times k is greater than W. So it clips at W. And those are two simple operations, but coming together, they can give you image normalization. And the image normalization, let's take you through this. It's occurred in the past, so it could be an interesting topic for examinations. Right. Step 1. Obtain the image histogram, which is a histogram of the number of pixels and the intensity. In previous exam questions, it will be 4 bits resolution, so the intensity ranges from 0 to 15, 4 bits. And of course, this is black and this is white. And because there most probably will be values at the origin, I always offset the horizontal axis away from the vertical axis. So this is 0 for the horizontal axis. And the intensity, the histogram is a histogram of intensity against pixels, and it will look something like this. And this would be an intensity, and this would be a number. It tells you the amplitude of each histogram entry is going to be the number of pixels at that intensity. So if we add up all the entries in the histogram, it should equal the total number of pixels. And that would be a histogram for an image when none of the pixels are absolute black and none are absolute white. It's in a relatively narrow range of intensity values. We can improve the quality by normalization. We need to detect the minimum pixel, Gmin. We need to detect the maximum pixel intensity, Gmax. And in image normalization, 1, shift Gmin to 0, black. What this means is we're simply shifting the histogram down so that this entry is at 0 and all the rest are shifted proportionally. Second step, multiply. And the multiplication factor, here the k in the shift is minus Gmin. And the multiply, k is going to be equal to the shifted high intensity, which will be Gmax minus Gmin, W divided by Gmax minus Gmin. And what this is going to do on the shifted histogram, the bottom will remain at black. You're multiplying by this constant. If the pixel value is 0, it remains there. And all the rest are proportionally shifted up. And the maximum pixel value will now be at absolute white. So the result of those two together, we will get a histogram which will go from 0 to 15. And the entries will be, there'll be an entry at 0, there'll be an entry, this one will be at 15, and we will have all the ones spaced out in between. The important thing is we're covering the full range. So that's got the histogram number, and this is intensity. Now, some people in the past have just left the answer there. There is the normalized histogram. That is not an image. And the whole point of this is to get a better quality image. So the next key thing is the pixel update table. And the pixel update table is to get the value of the pixels in the original image and the value they become in the enhanced image. So it will be the input and the output. And I can give you the limits quite easily. You'll have to work out the ones in between for a given example. And stop there. G min on the input, which is the pixels here, they will go down to 0. They will be absolute black. You'll have all the ones in between, 2, 4, whatever. G max in the original histogram, that point there, will become W, which for 4 bits is going to be 15, call it white, and you will have all the values in between. And so you then take the original image, read the input pixel value, replace it with the output pixel value, and that will give you an enhanced image. Now we've done an example in the lectures. Thinking of exams, if this were a question in the exam, you would have your original, your unique data. So data in exams, you might be given a 5x5 image. Let's draw roughly 5x5. Supposing your student number is 1743689. You might be told to fill in the array starting from the top left horizontally with your student number. Whoops. And so in this case, it would be 1743689. 1743689. 1743689. 1743689. And so that would give you each a personal picture to play with. There might be a shift to get the picture slightly brighter. Clearly, if you were doing this in an exam and the image came out to have a value at 0 and a value at 15, the limits, you can't normalize that. That's already normalized using the full range. So make changes so that G min and G max are not the limits, and then you normalization. I think there might be a condition, should this be an exam question, to shift the ones, add 2 or 3 to this, and then you would have a range which will be less than 0 to 15, and that's fine, and demonstrate the strategy should that be a question. Right, then there is taking this one step further for equalization. And equalization is minimization in band, normalization in bands. So, and again, should an exam question come up, it would be no more than 2 bands. We also have window operations. How am I doing for time? Gosh, time is catching up on me. Window ops, and the simplest one, come on. low pass filtering, smoothing the image, and the window operator. Nobody can forget this one. It is an array of 3 by 3 and all the coordinates are 1. You correlate that on an image, i.e. pass the window over a big image. So there is your window operator. And the output is the image is at the position of the center pixel. So make it a bit bigger perhaps. So that pixel there is equivalent to the center pixel there. And for very simple exam questions, a 3 by 3 window will give you 1 pixel at the center. You will lose the edges. Very drastic in low resolution pictures, but one never uses it on low resolution pictures. Larger images, 4,000 by 4,000, the loss of the top and the bottom rows, totally irrelevant. So don't worry about size reduction on simple examples, is to be expected. The key thing about low pass filter normalize, the correction factor, let's call it the correction factor. And you can see if this window is looking at white and we are adding the window multiplied by the image, clearly it's going to be the pixels in the image. They're all going to be added up. Maximum is 9W. So we can have a pixel value of 9W. It's impossible on a fixed image resolution. So we have to correct it, divide by 9. Every pixel in the filtered image. Then we come to the high pass filter. And the high pass filter, similar principle, but a different set of coordinates. And the simplest high pass filter, -1, -1, -1, -1, -1, -1, -1. All the edges are -1, but the center is +8. And that will enhance the sharpness of the image. And the range resulting from this is, in theory, -8W to +8W. But those limits are very rare because they are -8W, for example, would be a white area with a black pixel in the middle, and +8 would be a black area with a white pixel in the middle. And those are unrecognizable to the human eye. They are not significant features of the image. So if you normalized on that range, and I won't give you the equation because I don't want you to use that, if you normalized on that range, you get a poor quality image. So what you actually have to do to display a high pass filtered image is to normalize G-min to G-max, the standard normalization algorithm. So G-min goes to 0 and G-max goes to W. And that will give you a filtered image. And then finally, to complete it, I've got 2 minutes left, the edge detectors. And these are a class of windows. They start off with the simplest, which is the Roberts. I tend to draw them as 3 by 3 windows with zeros in, but some of the papers on the web will just give you a 2 pixel window for them, ignoring my zeros. And this would be H. And the coordinates for the vertical are -1 and +1. All the rest are zeros. The horizontal windows are -1 and +1. All the rest are zeros. And the result of correlating that image will give you an EV. This will give you an EH, the horizontal and the vertical edge stretch. You combine them. Either E total is going to be the square root of EV squared plus EH squared, or approximation mod EV plus mod EH. And that's the general principle of getting an edged image. The Roberts is the simplest, the Pruitt is a bit better. And this takes into account diagonals. And for the vertical, it is going to be +1, +1, +1, -1, -1, -1. That's the horizontal, sorry. And for the vertical, is going to be -1, -1, -1, +1, +1, +1. The other cells are zeros. Same combination, same thresholding. And for the Sobel, which is by far the most popular of this type of edge detector, the diagonals are weighted slightly differently, and for the Sobel, the weights are for the horizontal +1, +2, +1, -1, -2, -1, and the vertical -1, -2, -1, +1, +2, +1, and the zeros. And it doesn't matter if you get the pluses and the minuses the wrong way around, as long as all the coefficients in a row, in this particular case, are plus and minus. If these were all minus and this was all plus, it would still work. It would still detect an edge. And the same is true here. But you can't mix up the pluses and minuses in a row or a column. So that broadly is the edge detection algorithms. And at that point, I've run out of time. Hope you've got something out of that. Now, as Tatiana said, have a break. It's been a hellish year. Do actually, when you're revising, do use pencil and paper. Do write down things. Do try and remember and explain things without looking at the recordings, because it's so easy to look at the recordings and think, oh, yes, I know that, and it hasn't gone in. And a good test of that is if you think you can remember what's going on from looking at a video, write down a paragraph describing the last Netflix video you looked at, and you'll find it's pretty difficult. But if you'd written an essay about that content, it would be in the brain and you would understand it better. So don't skim over the recordings, actually think about it and get it into your brain, either by talking to each other or writing things down. Good luck. I won't be around for the next week because I'm taking an email holiday. But after that, please get in touch, and we most probably have another revision session at the beginning of next term. So have a good break, and bye for now. Any questions? Silence. Okay, then stop.